Thanks so much for the invitation. Thanks everyone for coming. Hi. So I'm going to give a talk. Please stop me and ask questions if you have any questions. I mean, I really like that when it happens. Okay. So I'm going to start. This topic may be slightly distant for some of you, but I hope everything will be very concrete and clear soon. Okay, great. So I'm going to talk about tensors. So tensors are, so for me, are just three-dimensional matrices. So we have, so we're working over a field F, and we're looking at n cross n cross n tensors with entries in F. And the main topic that I want to talk about is the notion of rank for a tensor, generalizing our familiar notion of rank for a matrix. Okay, so what is a good notion of rank? Okay, and I will list a few commonly studied ones. So unlike the matrix case, there are many competing definitions of rank for tensors. They all have nice and interesting properties and uses, and things get things get much more complicated with tensors. And so I'm going to introduce a bunch of these notions now, uh, and and in the talk I will introduce one more notion, which would be the geometric rank, and I will use it to, I will talk about the relationship of geometric rank with other ranks, and and then use it to talk about something called the subrank of matrix multiplication if I get time at the end. But anyway, please stop and ask me questions if you do. So I didn't say that. All this is joint work with Guy Moshkovitz and Jeroen Zuiddam. Okay, great. So let me start with the most basic notion, which is the most popular notion of tensor rank, which is often called rank. And okay, so I'll call it here tensor rank. So standard tensor rank. It is the smallest number of rank 1 tensors that you can uh, write your given tensor as a sum of. So standard tensor rank, uh, R of a tensor T is the smallest little r such that T is equal to the sum of ui tensor vi tensor wi, I going from 1 to r. Okay, so this is the outer product of three vectors. And okay, so this is, yeah, this is, a nice definition. And this is what is called the tensor rank, the standard notion of tensor rank. I'm going to introduce a few other definitions too. Okay. Good. So then let me mention a few other words, and then I will tell you what the definitions are. So there's going to be subrank of a tensor T. There's going to be analytic rank for a tensor T over finite fields. And the final notion I'll talk about is slice rank of a general tensor T. And eventually I will define all these things, but for now I just introduced this notion of rank, which is the most popular. Okay, so one of the basic questions in complexity theory, I'm not going to eventually answer this, but one of the basic questions of, or even move towards this is find an explicit tensor T with large tensor rank. And what is large here? So just to calibrate, this notion of rank is for a three-dimensional tensor. How large can it get? Well, there are n cube entries in a tensor. There are 3n entries in every term of this sum. So you need about n square, theta n square terms in the sum in order to have enough parameters to reach every tensor. So n square is the theta n square is about the largest a tensor rank can be. And okay, finding an explicit tensor with tensor rank around theta n square would be amazing. And even far from that is already the following open question. To find an explicit tensor rank with tensor rank little omega, little omega of n, or even eventually, I mean. And this is a famous open question in complexity theory, and and it is a motivation for a lot of results. There is a specific tensor which is extremely interesting, which people study a lot, which is the matrix multiplication tensor. I'm going to talk about that. The matrix, the m by m matrix multiplication tensor. This is the tensor that captures the complexity of matrix multiplication. So it is an m square by m square by m square tensor T. Maybe this is m sub m, whose okay, whose ij, okay, I need to specify the entries carefully. Okay. Good. So that whose ij kl, no, jk, oh yeah, kl, I should tell you kl, kl rs entry is 1. It's 1 or 0, and it's 1 only if j equals k, l equals r, s equals I, and 0 otherwise. So it is if these are like each entry is an edge. There's a hidden complete tripartite graph that I didn't draw here. There's an m tripartite graph here. Okay, this is m by m by m. And if you have 3 edges, one here, and one here, the corresponding entry of the tensor is 1 if those 3 edges line up to form a triangle. This is the matrix multiplication tensor. It is it's an extremely important tensor for algebraic complexity, because the tensor rank of the matrix multiplication tensor governs the complexity of matrix multiplication by algebraic algorithms. So this rank of mm is about m to the complexity of matrix multiplication. Oh, not complex, the exponent of matrix multiplication. So I'll say, okay, I'll write it as omega. Omega m to the omega is the complexity of matrix multiplication. And it's a very famous open question whether omega can equal 2. Right now, omega is 2.37 something, and it's been reducing in recent years. And but its derivative is approaching 0. This is my understanding with respect to time. Okay. Good. So I told you a little bit about tensors. Okay. So now that okay, so one of our friends in this talk will be the matrix multiplication tensor, but I'll come to that at the very end. So I'm now going to spend some time introducing the other notions of tensor rank, and after that I will define this notion of geometric rank of a tensor. Okay, are there any questions? No? Okay, great. I don't, oh, there's nothing in the chat. Okay, good. So I don't really know how anything is going. So for the moment, I'm just talking to myself. So just to distinguish this from that, okay, anyway, think of a question. I would appreciate it in the next 5 minutes. Okay. Good. I see. Yeah. Hi. Okay, good. Now let me define the notion of reducing one tensor to another. Okay, so given matrices A, B, C, I'll define the action A, B, C on a tensor T. Okay, T. So these are all in n by n matrices, and the action of this tuple ABC on T. Okay, this is not a group action because the ABC need not be invertible. A is, so the tensor T it's a cube, right? And it has slices. So let's look at the slices. There's this slice, and there's the next slice, there's the next slice. We can take linear combinations of these slices and leave them as slices. You understand? So I take a certain linear combination of these slices and produce a new slice. I take another linear combination of these slices and produce a new slice. That's what A does. A acts on slices in one direction, takes linear combinations of them, and replaces the tensor, produces a new tensor by taking certain linear combinations of the slices in this direction. Similarly, we have another matrix B. B acts on slices in another direction, these slices. How do I draw this? Oh. Yes. B acts on the slices in this direction, takes linear combinations of them, and produces more slices in that same direction. These actions commute with each other. If you act first on these slices by taking linear combinations, and then to act on slices in this direction, then whether you did this first or this first doesn't matter. There's an explicit formula one could have just written for what this action is. So this action, I want to consider this action, and we'll say T reduces to S. So this is the definition. If there is some ABC such that ABC acting on S equals T. What is this definition saying? So remember, ABC need not be singular. Need not be non-singular. They could be singular too. So they can reduce dimension, reduce the rank of things. This is a statement saying that you can it says that you can embed T inside S after taking linear change of variables in either direction. So that's what it says. I want to just highlight what this means. So rank of a tensor. So here's a fact, and this is an exercise in the definition we just did. The rank of a tensor is at most R if and only if T reduces to the diagonal tensor of R by R by R diagonal tensor. So this is, how would I say this? Yeah, so this is R by R by R, identity tensor. I'm stating this as a fact. What is the, so this is the tensor which is R by R by R, zeros everywhere and ones on the diagonal, on that principal diagonal. So that if the tensor reduces to IR, then the rank of T is at most R. This is what this does. Just to see the translation, I mean, if you write T as summation UI tensor Vi tensor Wi, then the matrices ABC you take are the A is going to be all the U's, B is going to be all the V's, and C is going to be all the W's arranged appropriately. Okay, so this was this is called the Gaussian order on tensors. So I define the Gaussian order, and the tensor rank shows up naturally as the smallest r for which T is at most IR. Okay, good. So now I can define the subrank Q of a tensor T. This is the largest N, or let's say the largest Q, such that IQ reduces to T. If you can embed, this is like finding a copy of the Q by Q by Q identity tensor inside T after a linear change of variables on the three sides. That's what the subrank is. This is another notion. How big can the subrank be? Yep, you said something?
N.
N, that's right. The subrank of a tensor can be at most N. The rank of a tensor can go up to N squared. Subrank is a different notion from rank. The two-dimensional versions of these things instead of three-dimensional, if you talk about two-dimensional versions, subrank and rank are the same. And I didn't define what subrank is in the two-dimensional case, but it's linear changes of variables on either side. Subrank and rank are the same. But in 3 dimensions, subrank is something which is at most N, and the rank is something that can go up to N squared. These are very different notions. Okay, this is subrank. Subrank is also an important quantity that comes up in the study of tensors, especially and in circuit complexity of things related to that. Okay, so this is the other notion, subrank. I'm not going to define the other two notions of rank. Slice rank and analytic rank. So let me do slice rank now first. Slice rank. Okay, so slice rank is a notion that was recently defined by Tao in his version of the proof of the cap-set conjecture by Ellenberg and Geisweit. So it's a very compact notion, and it's very closely related to these notions of rank. So the slice rank of a tensor T is the smallest S, such that T is sum I going from 1 to S of things of slice rank 1. Okay, and so Ti, where each Ti is of the form UI tensor. So this is a one-dimensional thing, and then maybe there's a matrix Mi, and similarly. Okay, so the middle term I don't know how to call it. I'll also say MJ tensor WJ, and then there's another thing which, okay, fine, my notation wasn't good, so, and there's a third kind. Okay, good. Okay, this is slice rank. Slice rank, the theorem of Tao about slice rank, which makes the cap-set conjecture, which plays an important role in the study of the cap-set conjecture, is that the subrank is at most the slice rank. If inside your tensor, so actually the actual statement was, if inside your tensor you have inside it a diagonal tensor sitting inside your given tensor T, if you have a diagonal tensor of dimension Q, then the slice rank is at least q. That's what the actual statement was. But since the notion of slice rank and subrank are invariant under linear transformations of the three sides, you also get the statement for subrank. Subrank is just a basis invariant version of the largest diagonal tensor contained within your tensor T. Okay, so this is slice rank. Okay, and finally, analytic rank. The analytic rank, it's defined only over a finite field, and it has a really strange definition, but it's again a definition of matrix rank for matrices. And so yeah, I mean, it's strange, but it is, I mean, it's a way of capturing matrix rank. And yeah, and it has many applications in additive combinatorics, as I guess this or the audience of this seminar, I mean, knows very well. Okay, so the analytic rank of a tensor T is so its original definition is in terms of you have so it's omega to the T of x, y, z. Good. So let me explain what this means. So omega is a q. Well, let's say q is prime for now. This is overall x, y, z in fq to the n. We view T as a trilinear form, taking x, y, z as input. You apply T to all those three. Take uniformly random x, y, z in fq to the n, and take omega to the power of that, where omega is a qth root of unity. So this measures the bias or the uniform distribution of the output of T of x, y, z under uniform x, y, and z. This is that's what analytic rank is, and it's also equal to the size. Okay. Oh no, log. It's log to the base q of minus log of this. Yep. And it's also equal to the size. So we look at the set of all x, y such that T of x, y dot is identically 0. Okay, that's a set. We look at the size of that divided by q to the n. Oh, maybe q to the 2n. And we take the log minus log of this. So this equality is just verification. There's some games with the q through to unity. And good. And this is the analytic rank. It's a generalization of the fact that sorry. It's a generalization. It's inspired by the following observation that for a matrix M, look at the set of all x such that x transpose M is 0. This set is the size of this set is q to the n minus rank. Generalizing that, this is a natural generalization of that. Okay, so these were some notions. Let me tell you a few things about relationships between these notions. Okay, so first there's qt, and there is the rank of a tensor. These are smaller than each other. I said that the theorem of tau was that slice rank lies in between. Okay, and slice rank is also at most tensor rank, just because so slice rank is at least subrank was the theorem of tau. Slice rank is at most general rank is just because every term in the decomposition of the tensor in the slice rank also has, is also standard tensor rank at most 1. Oh no, the other way around. Every term here is at most this. There's also analytic rank sitting somewhere here, right? And the theorem is good. So there's another. I didn't leave. I left too much space on one side, which I didn't mean to. Okay. Analytic rank of this. Wait. This is subrank. This is analytic rank. Hang on a second. Good. So I'll write in separate inequalities. The subrank is also at most the analytic rank. This is a theorem of Lovett. Also, analytic rank is at most rank times log of 1 over 2 over p minus 1 over p square. This gives a lower bound on analytic rank. So this gives a lower bound on standard tensor rank. This is a theorem of Brushundi, Harsha, Puya Hatami, Mrinal, Kumar, and myself. And good. So I think these are the relationships between these ranks. There are good. So these are a whole bunch of ranks that are related to each other. There is now I'm coming to the definition of geometric rank. Okay. The study of geometric rank was motivated by studying analytic rank. So let's go back to the definition of analytic rank and look at it again. We're looking at the set of all xy where you look at t of xy. So this is a trilinear form. We've already plugged in x and y, and we're hoping for it to be 0. Okay. So the geometric rank just looks at that definition and notices that the set of xy where this t of xy, where t of xy dot is identically 0, that is an algebraic variety. It's defined by a set of equations. These are bilinear equations on the x and y. Consider that variety and look at its dimension. And its dimension, should say something about the size of this set. So let's just consider that dimension. Okay, so I now possibly scratching whatever was done before. Here is just a definition: geometric rank of a tensor T. So the geometric rank of a tensor T is look at the set of all x, y such that T of x, y dot is 0. This is some variety sitting inside, and I would, just to be really, we look at an f bar to the 2n. Okay, so I went to the algebraic closure. This notion I'm only defining. It doesn't depend on whether you took extensions of the base field or not. Okay, and this is some set, and we look at the codimension of this. Okay, so it's sitting inside the space f bar to the 2n. Okay, and this is the definition of geometric rank. Okay, so let me make some quick observations about it. Any questions about this definition? The way we arrived at this definition is we were looking for a characteristic 0 analog of analytic rank. That's it. The definition of analytic rank amongst all these ranks, the analytic rank is one which only has a definition of finite fields. And we were looking for a characteristic 0 analog of it. And Okay, and this was a quantity we considered. Okay, and good. So now I'm going to make some definition, or I'm going to make some observations about this, and we will relate it in many ways uh, to the notions of rank that we've seen already. Questions? Questions about the definition? Uh, no? Okay. Great. So, okay, so the first observation is that the geometric rank does not depend on the fact that we plugged in x and y into the first two coordinates. You could also look at the set of all x, z, such that t of x dot z equals 0. And that's a potentially different variety that you get. Oh no, it is a different variety, but it may have a different codimension. And the statement is no, it has the same codimension. The definition does not depend on the order. GR. So just very explicitly, let me write it out. So this was, I mean, if the slices of T are M1, etc. up to Mn, then we're looking at a variety of the form x transpose mi y equals 0 for all I going from 1 up to n. We have a whole bunch of bilinear equations in x and y. This defines some variety. That's it. Okay, now the observation is, it doesn't matter how you slice the tensor, this variety still has the same codimension. Okay, so this definition of GR does not depend on the, I guess, order of the three coordinates. Okay, so I'm going to prove this. Good. So, but before I prove it, let me tell you what our main results are. So results. The first is the geometric rank is an upper bound on subrank. Just like all the other ranks that we saw. The subrank was the smallest. Geometric rank also is large, at least as large as the subrank. Okay, so this is 1. 2. The geometric rank is, I mean, the set of all tensors of geometric rank at most R is closed, is Zariski closed. So the set of all T such that geometric rank of T is at most R is Zariski closed. This means in particular that there's another notion called the border subrank, which is which is an approximation version of the subrank. It talks about the largest subrank you can achieve by tensors that go arbitrarily close to T. And this is also at most GRT. So yeah, so the geometric rank is also an upper bound on border subrank. Okay. Third is that the geometric rank of matrix multiplication is equal to 3m square over 4. This is an exact formula, and it matches the upper bound of q bar t being at least 3m square over 4. This is by Strassen from the 80s. So this gives an exact formula for q bar t, q bar of the matrix multiplication tensor. Okay. Final. Okay, and so other relationships. The geometric rank of the tensor is at most the slice rank of a tensor. And finally, geometric rank is like a characteristic zero analog of analytic rank. So geometric rank of T. So, okay, so this is the final statement. So this has to be said carefully. If T has Z entries, or I guess Z entries, then look at the analytic rank of T mod P. This is, okay, so what would have been amazing is if this was equal to the geometric rank of T. So this is not true. What would have been almost amazing would have been the limit as P approaches infinity of the analytic rank of T mod P equals the geometric rank of T. That would have been also pretty amazing. But unfortunately, the only statement that we were able to prove, although we can't we don't know that this limit, it can't be a limit, is that this is the limit of this. So if you take a tensor over the integers and you look at it mod P, and you look compute the analytic ranks that you get, then as P goes to infinity, then the analytic ranks, yeah, they infinitely often go to the geometric rank. They can go higher, but good. So these are the statements. I will, okay, so now I will talk about some of the proofs. Are there any questions about what I've said so far? So it really suggests that geometric rank, so geometric rank also lies between subrank and slice rank. It's a friend of analytic rank. So I mean, it really, and so just like analytic rank lies between subrank and slice rank, and it right, geometric rank and analytic rank are really good friends. I think that is that's sort of the headline of everything. And a very recent result by two independent groups. So one is by Cohen and Guy Moshkovitz, and another is by Adi Prashito, Ziegler, and Hrushevsky, is that analytic rank, geometric rank, and slice rank are all within a constant factor of each other for three-dimensional tensors. So this is a very recent result. It's been on the archive for less than 2 weeks, I believe. So and it's very clean and very neat. And I mean, so the notion of geometric rank hasn't been around much, but the other two ranks have been around a lot. And whether they were within, I mean, the relationship between them has been studied extremely heavily. And there were many recent, so I don't know the exact literature on that, but I know that I believe a lot of the audience, at least I see some names in the audience, Luka Milicevic, for example, where who studied the relationship between them, and there has been a lot of progress on studying the relationship, and I think for three-dimensional tensors, the tightest relationship has recently been found by them. Okay, good. So I'm now going to say some things. I have good. I guess I have about 15-20 minutes.
Oh, there was a few questions in the chat. I don't know if you already.
No, I didn't see. Oh, good. Okay. For this talk, I'm only talking about three-dimensional tensors. Lots of results work for four-dimensional tensors, 4 and higher dimensional tensors too. So let me see. This general inequality holds for all dimensions. This general inequality holds for all dimensions. There is no matrix multiplication tensor. This also holds. This also holds. Yes. So lots of things hold. But the statement about matrix multiplication, I mean, that's unique to three dimensions because there's only a three-dimensional matrix multiplication tensor. Okay. Other questions? So I can, in principle, show you a lot of the proofs. Everything is very, very first principles, and all proofs are very, very short, right? So okay, so let me tell you some things. Okay, okay. First, so it will just be a bunch of observations about geometric rank, and at the end they'll just arrange themselves into proofs. So the first observation is that the geometric rank of T1 direct sum T2 is equal to the geometric rank of T1 plus the geometric rank of T2. What is direct sum? Well, direct sum for matrices is I have a matrix, I make it a block diagonal matrix. Good. Now I similarly make a block diagonal tensor where there's going to be lots of zeros everywhere, and there are two blocks. The first one has T1 and the second one has T2 along the diagonal. That's this. And the proof of this is just inspecting what is that set, what is that variety whose codimension we study when we look at this. Okay, so T1 gives you a bunch of equations on a small set of variables. T2 gives you a bunch of equations on another set of variables. And then we're looking at the product of those two varieties. And the dimension of the product of two varieties is the sum of the dimensions. And that basically explains this. Okay, so I just wrote that without saying. Okay, so dimension of product of varieties. Okay. Good. Oh, good. Actually, even before this, maybe I should tell you why the geometric rank does not depend on the order of the three coordinates. That's actually, that's even more, I should have said that first. We're looking at the set of all x, y such that t of x, y dot is 0. Okay. Then I want to write this. I want to break this setup according to the x. Okay, so here is the space of, this is all f to the n. This is the space of x's. So this was x, y, and f to the 2n. Over an x, what are the y's for which x, y lies in the set? Okay, so given x, what is the set of all y such that t of x, y dot is 0. Okay, so this is just the same as the set of all y's such that the set looks something like this. X transpose mi y equals 0 for all r. X transpose mi is just a vector. So this is a bunch of linear equations. So the set of all y's which has this property is a linear space. Okay, so it's which linear space? So it's a linear space of dimension rank, or so let's say co-rank of x transpose m1, x transpose m2, x transpose mn. You took all these matrices m1 up to mn. I didn't mean to strike that out. That was you took all these matrices m1 up to mn. We multiplied them all by x. We got a whole bunch of column vectors. We took the co-rank of that, and that's the dimension. That's this. The space of, that's the dimension of the space of y's that satisfy this. Okay, so how many y's are there? Okay, I want to say how many. So what's the dimension of the y's that have this property? Well, it is the co-rank of this. Good. So there's a natural way to understand the dimension of this variety by breaking it up in cases on the x's. Look at the x's for which this co-rank is a certain I. For those x's, maybe there's a j dimensional space down here. Above each of the j dimensional spaces of it's not a space. There's a j dimensional set of x's such that over each x in that j dimensional space, there is a codimension I space of y's sitting there. So this helps you understand the dimension of the entire variety by breaking it up. So I'm going to write that down now. So we look at the dimension of the set of all x's such that this, by the way, is just it's a certain matrix. I'll tell you what matrix it is. It is the matrix T of x dot dot. T of x dot dot is a two-dimensional matrix. It's a bilinear map in the two entries, so it's a matrix. Look at that, and let's look at the rank of that matrix. This is good old matrix rank. Set of all x, so it's the rank of T of x dot dot is equal to I. Okay, this is a set of x's. It's not a linear space, but it's some set of x's, and we look at the dimension of that variety. So it's in fact not even a variety. It's a horrible set. It's the set of all x's for which a certain matrix whose entries are linear forms in X have a rank equal to I. At most I is okay. At most I is defined by a set of equations. Equal to I is a set of equations and inequations. So that's a bit of a worse set. But okay, it's still a thing for which you can compute its dimension. It's a locally closed set. So it has a dimension. We take that dimension and we good. So we take that dimension. So that partitions the space down below into pieces. Each piece has a different size of fiber above it. And okay, and then just by studying these fiber dimensions, you can understand so the fiber dimensions and the dimensions of these, you can understand what the dimension of the whole variety is. Okay, so I will just write down a formula for this. So the dimension of the set of all xy such that T of xy dot equals 0 is equal to, okay, so we break up this thing into pieces, and each piece has a dimension, and the dimension of a finite union of, not varieties, but things. Yeah, the dimension of a finite union of things is the maximum of the dimensions of those things. So I write that down. This is the max overall I of the dimension of the set of all x's such that rank of T of x dot dot equals I. That's the dimension of the x's down below, and the dimension of the space above it plus n minus I. N minus I wrote here co-rank, and here I wrote rank, so that's why there's an n minus instead. And this is exactly good. So if I want codimension, right, and so this whole thing is 2n minus the geometric rank of T. And this expressed the geometric rank in terms of just one of the variables x. It doesn't depend on whether it was y or z we took in the definition. So just by exact symmetry, this is the same as the dimension of the set of all x z such that t of x dot z equals 0. So this definition does not depend on the fact that we took x and y. We could also take an x and z. So we could similarly have taken y and z. So it doesn't depend on the order of the coordinates. Okay, so that was maybe one main observation. Okay, so I didn't say much more. Okay, good. So, and I'm also almost out of time. Am I almost out of time?
A few more minutes.
A few more minutes. Okay. So. Okay. Fine. Fine. I'll say one thing. Where a thing is a big object, right? So I'll show you that geometric rank of T1 plus T2 is at most geometric rank of T1 direct sum. Oh, is at most geometric rank of T1. It's the subadditivity of geometric rank. Okay, okay. Actually, since I have a small amount of time, let me just say high-level things. Okay, the proof of this. Okay, so all the proofs are extremely short. I recommend you look at the paper. The proof of this is all the proofs are extremely short, and they use very simple properties of geometry of dimension and codimension, and they don't use. There's nothing heavy going on. The computation of the geometric rank of matrix multiplication is just understanding this. It goes through this characterization of geometric rank in terms of studying ranks of things. Okay. Let me just talk about the final statement, and this is a really nice question. The analytic rank, if you remember, measures the size of a certain set, the set of all xy's for which t of xy dot is 0. It measures the size. Geometric rank talks about the dimension of that as a variety. The dimension of the variety should determine the size of that set if that variety is generally nice. In this characterization or in this formula, we did use the fact that for a variety defined over complex numbers, if you reduce it mod p, you get if the original variety is, say, absolutely irreducible over the complex numbers, and you reduce it mod p, then for many p's you will get an absolutely irreducible variety. Oh, sorry, for all large p's you'll get an absolutely irreducible variety. But right, but it may depend on some algebraic numbers like square root 2, for example, being in the field. So the reason we only get a lim-inf here instead of a limit is that I mean, whatever algebraic number like square root 2 we may have depended upon for the dimension being small, that square root 2 may not exist in the field fp. So it's true that for infinitely many primes p, square root 2 lies in the field fp, but not for all primes p, or even all sufficiently large primes p. So I think there's the question of whether this can be a limit instead of a limit, I think is a really nice question. Anyway, good. Maybe that's all I have to say now. If there are questions, I can